Hello, good morning, good afternoon, and good evening. My name is Samuela Guida from the International Water Association, and I welcome you to this second day of the PrimeWater Multi-User Panel Stakeholder Week. Today, we focus on disaster risk management. So some housekeeping rules before we start. If possible, I ask you to rename yourself with the name and your company. And then just as a note, please remember that the meeting will be recorded. If you have any concern about this, please contact me. You have my email address there. We ask you to please show your video as you wish, but please mute your microphone where you're not speaking. And for each presentations that we will have today, please add your questions in the chat box that you find just below. And if it's possible, please indicate the name of the presenter you are addressing, so it's easier for the moderator to understand. And then after the meeting, you will receive the slides and the recording of this session. The recording of yesterday is already on YouTube, if you want to check that out. So I was saying this is the PrimeWater Multi-User Panel Stakeholder Week. So what is the multi-user panel? So the European project PrimeWater has a multi-user panel, which aim is to serve as an international panel of users, providing expert feedbacks on the Earth observation enabled services developed or extended in the context of PrimeWater projects, and also to participate in the co-generation process through dialogue. So the first MUP workshop was in October 2020, and we gathered initial feedback on what different users think about the services that PrimeWater is offering and other different services. This second MUP, we are planning it as a stakeholder week from the 15th yesterday to until Friday, 19th of November. And each day we'll have a 2.5-hour session on a different topic. Yesterday, we had the water resource management session. Today is disaster risk management. And over the week, we will talk about potable water, energy sector. And then finally on Friday, we will close off with amenity, recreation, and aquaculture. The main objective of this week is to provide to you and all the participants an overview and update on the services that PrimeWater can offer, to understand how different sectors are using Earth observation services to address issues such as extreme hydrological events or harmful algal bloom, and then to discuss the added value that PrimeWater products can have when addressing these issues. Today we have kind of a packed agenda. We'll start, the session is divided in three parts. So we have an introduction with where we will set the scene and discuss the PrimeWater platform. Then we will have two experts presentation moderated by Cindy Brass from US EPA. And then we will close off with a panel discussion where we'll be using a collaborative tool. And this session will be moderated by Catherine Cross from IWA. So we have prepared a little icebreaker pool for you, which I will start now. So on your screen, you should see two questions. Please indicate your sector and if you use Earth observation technologies in your work. You don't use it, you use it directly. So you use Earth observation in your work directly or indirectly use the products of Earth observation. So I give you 1 minute to complete that. Thank you. Perfect. Thank you so much. And if I show you the results, we see that the majority of people come from consultancy, then university research institutes, and then government organization and other. And then you use Earth observation, yes, directly, the majority, and then 20% indirectly, and no. So you can learn some applications here. Thank you so much for that. And Perfect. And I think with this, yes, I give the floor to Apostolis, which will set the scene of today.
Thank you, Samuela. Thank you all for being here with us today in this discussion, in this workshop about on how can you use Earth observations for managing water quality related risks in water from the disaster risk management perspective. And that's a very interesting perspective for our group that we would like to investigate with all of you today. I think, can I, right, okay. All right, it works. So this workshop is part of the PrimeWater initiative. As Samuel mentioned, PrimeWater is a project, is a research and innovation project funded by the European Commission, and is working on. It is about fresh water. It's about freshwater water quality, and investigates how Earth observations can be used to support water quality hazards reduction. Well, it becomes more or less to more global assessments of disasters and risks that natural born and hazards are climate or weather related and disasters. So there's a huge percentage then, as you can see in the slide, and of course water quality threats have a role to play in this field. Harmful algae blooms occur and can have a significant, severe impact across environmental and socioeconomic domains, with huge social and economic costs imposed to different actors. PrimeWater has been working the last 1.5 years on how to actually provide towards end users, towards decision makers, robust, reliable services for addressing those water quality aspects, those water quality hazards, and manage to reduce exposure and variability towards those risks. The emphasis on harmful algae bloom outbreaks, where it is most of the work is taking place. It's part of our work that we're doing, a strong scientific component, but at the same time, the major goal of our team is to provide towards the water sector applications based on those scientific advances that can really assist in everyday workflows. And talking about disaster risk management, the key component, the key service that PrimeWater is working on towards this direction has to do with an early warning, forecast-based early warning system for algae bloom, a solution that is powered by Earth observations in order to improve the skills in the forecasting capacity. So talking about early warning systems and forecasts, the main focus in terms of temporal, let's say, forecasting capability is on the short to medium term forecasting, so 10 days in ahead. And in order to do so, we have put together in PrimeWater complex, let's say, modeling chain, starting from hydrological forecasting and hydrological forecasting, that are fed, that their forecasting skill is improved using the observations, mostly Sentinel and Landsat satellite imagery, adopting and deploying different techniques, either through data simulation directly in the physics-based models, or using and implementing machine learning algorithms directly with those data. So those services will be presented immediately after this presentation in a short introductory video that will guide you through several components of this service, and how these can be used at the moment for decision making. So going back to the topics of today's discussion, which is about how to use these valuable, this new information, the forecasts. How can this information be used and trigger early actions from the perspective of disaster risk management? This is a very useful perspective with a lot of experience from working with other natural hazards that we are really looking forward to introduce into the way of thinking also when it comes to water quality threats and hazards in fresh water. And this is the purpose also of this workshop, and we'll be happy to have our invited speakers to share their insights on that. Having those forecasts, having a knowledge of how water quality can evolve ahead of time, what is really can be initiated is anticipatory action. So this is where an early warning, this is where these forecast by early warnings for HAB assessment aims, and our work is revolving around. There is strong rationale for doing so. Recent studies have revealed significant benefits from using observations in actually warning early enough people from not getting in contact with freshwater that they experience HAB outbreaks in terms of human health outcomes. There's a strong rationale for demonstrate the usefulness of these early warning systems also for HAB events, as it has been widely demonstrated in other natural hazards like floods, for example. So talking for early warnings, well, PrimeWater has been investigating a series or has went through a series of stepwise approach from nowcast-based early warning to forecasters described based early warning, both deterministic but also probabilistic forecasts in order to provide comprehensive and robust information for triggering early actions. This is the basis of the work that we're doing in PrimeWater, and hope that this will trigger a discussion later on among all of us that are taking place in this workshop. Well, wrapping up this very short introductory presentation, there is like to thank and let you know that there's a very strong team behind PrimeWater, working in all those different components, from the scientific components to the automated and the service components. And with that, I would like to thank you for attending this presentation and let you enjoy the short demo video that will follow. Thank you so much.
Hello, I'm Vangelis Romas from Envis, and I'm going to make a short presentation of PrimeWater's operational platform. The platform is available through a web browser, either through the PrimeWater's website or directly through the second link. This is the initial page of the platform with the 4 operational case studies of PrimeWater in Europe, United States and Australia. The PrimeWater currently offers 4 services, which are the EO-based monitoring system, the Hydrological Forecasting service, and the Water Quality Forecasting service, which is offered both by process-based and data-driven models. I will now jump to Melbourne Western Water Treatment Plant, and I will start with the EO monitoring service, which provides operational EO-based water quality products from Landsat and Sentinel missions. On the map here, we are able to see the latest available satellite image for our case study, which is for today, obtained just a few hours ago. The product shown here is chlorophyll A concentration at a resolution of 10 by 10 square meters. And by clicking on the map, we can read chlorophyll concentration at various points of interest. You may notice a gap here in the center of the map, which, as you can see in the true color image, is due to the cloud coverage. Apart from chlorophyll A, we are also able to quantify turbidity, total suspended matter, total absorption, shaking disk depth, and also a harmful algae bloom indicator, which classifies the probability of hub existence based on the presence of phycokianine pigments. Also, we are able to provide surface water temperature from Landsat. However, this product is not available in this case study due to the low resolution of Landsat at 30 by 30 square meters and the small size of the ponds, which causes a strong interference with the land boundary. However, surface water temperature is available on all the other case studies. In the calendar here, we can see the dates with available overpasses of satellites, and we can go back in time until 2015. Also, there is a useful tool for exploring the temporal variation of a parameter in a selected area. For example, in the graph here, we can see the historical turbidity values for the last 3 years at the selected point of interest. Currently, these EO-based water quality products are produced by EOMAPS processing algorithms. We also aspire to include algorithms from other remote sensing partners of PrimeWater, for example, CSIRO's processing algorithms. And we also aspire to include hyperspectral water quality products from Prisma and DESIS missions, although these products will not be available operationally, but only for historical periods. The next functionality of the platform is the Hydrological Forecasting service. I will now jump to Lake Hume and select the Hydrology tab. This service is provided by SMHI and the worldwide HYPE model setup. In the map, we can see Lake Hume and all its upstream hydrological catchments. These two contribute directly in the lake, and if I click in one of them, I can view the hydrological forecast for 10 days ahead regarding river discharges entering the reservoir. In the graph here, we can see hintcast and forecasted values of river discharge for today and the following 10 days. Apart from river discharges, the hydrological model provides also forecasts of nutrients, nitrogen and phosphorus, and suspended sediments. And those variables are a very important input for the water quality modeling that is performed inside the reservoir. The hydrological model offers both a deterministic and probabilistic short-term forecast. If I switch to the probabilistic forecast, then we still have 10 days forecast, but this time we simulate a hydrological ensemble of 51 individual model trajectories, as you may see in the graph. So, apart from the average ensemble value, we can have an estimation of possible range of values for each day, and we can calculate some useful statistics such as percentiles, which is a valuable input for quantifying and dealing with forecast uncertainty. There is also a third hydrological setup, which is available only in the European case study, which is a seasonal hydrological forecast, where we can have forecasts for up to 7 months ahead, averaged on a weekly basis. Moving further down to the modeling chain, we have reservoir water quality forecasting provided by ENVIS. This is the Moulargia reservoir in Sardinia, where we have used the Del 3D suite to set up a three-dimensional hydrodynamic model coupled to an ecological model. The hydrodynamic model is forced with meteorological and hydrological input and provides us the circulation pattern inside the reservoir and water temperature for the next 7 days. The map currently displays water temperature for the top layer on a grid of 100 by 100 square meters and 20 vertical layers. By clicking on the map, we can read temperatures at each cell. We can also visualize the water velocities with these nice animated arrow traces. And of course, I can move this time slider up to 7 days ahead in the future in 6 hours intervals. Actually, there is a nice tool that visualizes the evolution of the parameter in the forecasting period. For example, in the graph, we are now observing the diurnal variation of temperature in the topmost layer. As I said, we are using a three-dimensional model, so apart from the top layer, we are also able to get information for any depth we would like. For example, here, in the middle layer of the reservoir, the temperature variation is not so pronounced. Values are almost identical for the forecasting period. The vertical profile of each forecasted parameter can also be viewed in a separate graph for any selected point. For example, here the model indicates that there is a thermal stratification at the selected point of the reservoir. The parameters of the water quality model include chlorophyll A, nutrients, phosphorus and nitrogen, suspended sediment and dissolved oxygen. Here I have selected chlorophyll A, and the map and the graphs are now showing chlorophyll concentration. And finally, there is a third tool that allows us to view cross-section of any simulated parameter along the two main directions of the reservoir. Both in the hydrodynamic and water quality models, we are incorporating data simulation techniques that are using satellite-based products as well as in situ measurements to correct the model state and avoid error accumulation. So with the process-based models, we are able to expand the available information that we have for our reservoirs up to 7 days ahead in the future. And compared to the Earth observation, we can also have information at deeper layers and information about non-optically active parameters like nutrients. Apart from the process-based models, ENVIS is also employing machine learning models for forecasting chlorophyll and algae bloom events. So I will now move to our last case study, which is Lake Harsha. Data-driven models are trained for specific areas of interest presented as triangles in the map using meteorological forcing, forecasted nutrient fluxes from the hydrological model, and are compared against EO-based chlorophyll values or even in situ measurements, since in Lake Harsha we had some nice historical time series with a large number of chlorophyll values and cyanobacteria cell counts. We are currently using 3 types of machine learning algorithms: Gaussian process regression, random forest, and random undersampling boosting. I will stay in the GPR model, which predicts chlorophyll A concentration only in the surface layer this time. By clicking on a point of interest, we are able to read the chlorophyll values at the current time step. Again, there is a graph that presents the time variation of the forecasted parameter. The dashed line are the hindcasted values, the continuous line are the chlorophyll values for today and the next 10 days ahead. One nice feature of the machine learning algorithms is that they can provide us with some confidence levels. So for an 80% confidence level, we can see that the predicted values of chlorophyll A concentration increase from 4 micrograms per liter to almost 20, and even higher for the 90% confidence interval. I will now jump to the random undersampling boosting algorithm to present you a different type of product we are using for bloom forecasting. So this algorithm has been trained to predict cyanobacteria cell counts, but not as a scalar quantity, but as a probability of exceedance of a specific threshold specified by WHO. And we have made this choice because we have seen that the model has a stronger skill in predicting if cyanobacteria concentration are going to be over or under the threshold of 100,000 cells per ml, rather than in quantifying exact values of cell densities. So in the graph we can see that the model predicts that for the selected point of interest and the entire forecasting horizon of 10 days, we're having a no-hub situation with a high confidence level. While if I click to this point, then we see that we still have a no-hub situation, but this time with a lower model confidence.
Thank you. Perfect. So I'll now open the floor for some questions. You can write down in the chat or just unmute yourself and ask the question directly to Apostolis or Evangelos. If not, maybe I can kick off with one question. So I was wondering what type of meteorological forcing do you use in the water quality model?
Okay, yes. Can you hear me, Samila?
Yes.
Okay, this is Vangelis. Yes, well, in the water quality model, we are using the global forecasting system from NOAA, which is provided at 0.25 degrees and provides forecast for 2 weeks ahead at a time resolution of 3 hours. Of course, we are able to use also other forecasting services, for example, from ECMWF. And we can also use, depending on user preferences, even local or national for meteorological services. From our side, we have a very, let's say, flexible IT infrastructure, and we connect to virtually any provider and collect real-time information either through APIs or through FTP protocols.
Thank you, thank you. And if I can ask, what is the spatial resolution of the hydrological and reservoir modeling?
Okay, yes. Well, the hydrological modeling is performed at the catchment level. An average catchment size for the worldwide HYPE setup is about 1,000 square kilometers. Specifically for the case studies of PrimeWater, these models have been downscaled and recalibrated with local datasets. So we have reached an average catchment area of about 500 square kilometers. For the US and Australian case study, for the European is a little even lower. Now regarding the reservoir modeling with the process-based models, there we are using typically a cell size of 100 by 100 square meters, which of course depends on the total surface area and the shape of the reservoir. For larger reservoirs, we can go to lower resolution and vice versa. And this is always a matter of computational efficiency and model performance. And regarding the vertical dimension in reservoir modeling, we're typically using 15 to 20 vertical layers, again, depending on the maximum depth of each reservoir.
Thank you, thank you. I'll open again the floor to the participants if you have any questions or comments about what was presented. Please do not hesitate to ask. If not, I have another question about how many years of monitoring data sets are required for the training of the machine learning algorithms for the phytoplankton bloom forecasting.
Hi, Samuela. Perhaps I could, I'm Kyriakos Andris, first of all. I could step in to answer that. I can give you a rough estimate. Let's say we have a series of 6-year-long data sets, which on an average, I would say that this corresponds to, let's say, 150 to 2,000 cloud-free images. So this is a very, to get an inkling of the size of the data required, I would say that we can say that between 150 to 2,000 cloud-free images are required to build a credible model, and this corresponds, as I said before, to nearly 5 to 6 years of monitoring.
And okay, so so if I'm not an expert, so what's a cloud-free image? Just no clouds at all, so it's a clear image.
Correct.
Correct.
Correct. That means that's not contaminated by clouds, and we have access to pretty much all the extent of the water body without any quality associated risks.
Okay, all right. And the one final question that I have, it's about the forecasting horizon. And so is this the forecasting horizon common for all the forecasting services?
Okay, so for the hydrological forecasting services, we have a forecasting horizon of 10 days. So we're able to give information on hydrological quantities, river discharges, and nutrient and sediment loadings for the next 10 days ahead. There is also another hydrological setup, which is seasonal. So there we can have estimation for 7 months ahead in the future, average on the weekly basis. But this only refers to river discharges. So water quality parameters are absent from this seasonal setup. And then when it comes to the water quality forecasting, either through process-based models or through machine learning models, then we are again bound to 10 days ahead because we are using the hydrological forcing. So we are bound to 10 days ahead. And currently we have a 1-week forecast available through the process-based models and 10 days forecast available through the data-driven algorithms.
Okay, thank you. And I have just one final question before we go on a little break. So in the reservoir modeling, are you able to assimilate in situ measurements or only Earth observation-based water quality products?
Okay, actually we can assimilate both EO-based water quality products and in situ measurements. The EO-based water quality products are a very useful source of information for data simulation, since they provide a large coverage, a large spatial coverage of the reservoir. But we do also have some data simulation techniques like the ensemble Kalman filter that can take advantage of even single point measurements in the reservoir. So we can correct the entire modeling domain based on single point measurements. And actually the hydrodynamic models set up for the case studies of PrimeWater are using water elevation from a single point to correct the elevation, the water elevation in the modeling domain. The only concern with the in situ parameters are the delay that we have in their acquisition, because we need this information in real time or in near real time in order to incorporate it in the models. So if we have in situ measurements available within with a delay of 1 or 2 days to our systems, then we can take advantage of them. If the delay is longer, more than 2 days, let's say, then technically there is still a way to use it in data simulation. However, the expected improvement in the forecasting skill might be limited in such cases.
Okay. All right. So thank you so much, Evangelos, Kyriakos, and Apostolis for this very interesting presentation. The chat box is still open, so if you have any questions, please feel free to add them there. In the agenda now we have a short break. So in London is 1:37 GMT. So we'll come back at in 5 minutes. Is that okay for you? So at 1:43, 45. So yeah, so we come back in 5 minutes. Thank you again. Okay, everyone, welcome back. We will now move into session 2. The format of these sessions, we will have speakers' presentation and a moderated discussion. The moderator for this session is Cindy Lebras from US EPA. So Cindy, I'll give you the floor and hey, yes.
Okay, thank you, Samuela. So again, I am Cindy Lebras, and today I will introduce our first speaker, which is Mr. Carlos Uribe from the UN Office for Disaster Risk Reduction and the Regional Office for the Americas and the Caribbean. And he will talk today about the disaster risk reduction landscape in the Americas and the Caribbean. And Carlos, the floor is yours.
Thank you, Cindy. And I wanted first, on behalf of the whole UNDRR, thank you the organization of the event to taking us in account and to invite us to present today. I was hearing to the previous presentation and very impressed because I come from a very technical background, working with the European Commission on the definition of the actual Copernicus system. So I used it to work with the satellite technology for a long time. As Cindy said, my name is Carlos Uribe. I'm in charge of a specific portfolio on UNDR that is called the Risk Knowledge. And I'm part of the team that is based in Panama, covering the Americas and the Caribbean, 37 countries. And our main task is to support the countries of the region on the implementation of the disaster risk reduction framework, the Sendai framework for disaster risk reduction. Next slide, please. Just to give you an idea of the context where we are evolving as an organization, we did a study with the CRIT, the Center for Research on Epidemiology and Disasters, and ECLEC, about the losses. Oh, sorry, my first slide was in Spanish. I couldn't start that. I will talk in English. About the disaster losses globally. And particularly, I'm talking about the Americas where we're working now. It's very complicated context, taking into account that we concentrate 45% of the total losses, direct losses linked to disasters. Next slide, please. One other key information on the current context, not only for the Americas, but globally, is that in the last 20 years, the number of disasters, the number of deaths, the number of people affected, and also the amount of economic losses have doubled from 2000 to 2000 to 2019 in comparison with the previous period between 1980 and 1999. Next slide, please. One of the most important elements that we are supporting globally is, as I told you at the beginning, the mandate of the UNDRR office is the implementation of the Sendai framework for disaster risk reduction that has started in 2015 and approved by 193 countries in Sendai in Japan. But this framework is part of the 2030 agenda that includes also the Paris Agreement on climate change adaptation. The way we see the Sendai framework is as a connecting tissue between those three key elements on the SDG agenda. We cannot talk about disaster risk reduction without talking about climate change adaptation and vice versa. So we found that this is an opportunity to ensure coherence between these three agendas that will give a clear and substantial contribution to the obtention of the SDGs. Next slide, please. In the Global Risk Assessment Report and many papers that we have been producing with other organizations, we are communicating about the systemic nature of risk that is based on the interconnected and interdependent natures of the hazards we are facing globally. One of the priorities for us is to strengthen the understanding of this systemic nature of risk and all the possibilities and the scenarios that could be possible using the systemic lens, including the cascading and compound effects that could conduct us to what we call systemic failures. Next click, please. And one of the best examples of systemic risk is the current situation with the COVID-19 pandemic. And this is we use very often this as an example because we know clearly that disasters are socially constructed. So the way we want to reinforce the disaster risk reduction and disaster management way in the countries is taking in account the underlying factor of risk, analyzing the different contexts, analyzing the drivers, what is driving the risk and the manifestation of risk, that is the final disaster. So to understand the systemic nature of risk, we need to take in account this interconnected nature of different systems, economic, political, the environmental degradation, the missing of land planning, land policy, the economic and social models we are operating in our regions and cities. And also the context, where is that happening? That will determine the equation of risk, exposure, vulnerability, and hazards. For finally have a realization of the risk. But this is all the elements we need to analyze to understand, and we need to make sure we're tackling from the beginning for a disaster risk management efficient way. Next slide, please. We're producing now what we call a regional assessment report for Latin America and the Caribbean. We have produced in 2019 the Global Risk Assessment Report. Those reports are trying to give an idea of the state of the art of disaster risk reduction globally, and this one particularly for the Americas and the Caribbean. I wanted to recall the priority one of the Sendai framework for disaster risk reduction, that is understanding risk. And here is where the satellite imagery and space technology could contribute really to the implementation of these frameworks, particularly the target E of the Sendai framework for disaster risk reduction calls for the increase the number of countries that have national and local disaster risk reduction strategies. And the national and the local disaster risk reduction strategies are based on evidence, and this evidence is given by in situ data, satellite data, and all the information that could contribute to inform decision-making processes and the establishment of disaster risk scenarios. So here is the first point, and it's clearly mentioned on the paragraph 23, if I remember well, of the Sendai framework for disaster risk reduction, that we call for the use of the space technology and geographical information system to inform decision-making processes. Next slide, please. This is specifically for the Americas and the Caribbean, and one of the main findings we can highlight on this report is that the face of the cities of the region is changing. The climate effects are already started to be felt in the region. So the new patterns of the cities, the new patterns of urban risks are changing, and we need to take in account that particularly for the Americas and the Caribbean, we live in the more urbanized areas in the world. So now we need to take in account the climate change effects and all the effects of different phenomena like migration motivated by violence, conflicts, or climate change or disasters. But this is changing the landscape, and this is determining different levels of exposure and vulnerability in the cities. And this calls for a new way of management of the cities, and also the mechanism of governance at the national level, taking about the governance. Next slide, please. This is just to give you an idea of what is happening now and what is the contribution of climate change that is coming in addition to the old problems that the cities have. A clear complex context for the island of the Caribbean that are the population are concentrated not only in the cities but in coastal areas. So the new manifestation of the manifestations that are powered by climate change as fires, heat waves, fluid droughts, water stress, epidemics, and pandemics that are increasing a lot on the here in the region, but also globally. We have produced 6 months ago the Global Risk Assessment Report for Disaster Risk Reduction, a special report on drought that is talking about all the problems in California, the drought corridor in Central America, and the lightning fires in South America. Next slide, please. Part of the analysis we did within the regional assessment report in partnering with the Latin American Development Bank was about the public policy progress in the region. And we have analyzed 26 countries of the 37 of the region. And we found that they have a real progress on reforms in terms of public policy and governance mechanism in the region. Even if we are registering a very good level of progress on this, we found that investments and the budget allocation doesn't match. So we need to progress on the implementation of national and sectoral policies for disaster risk reduction with budgetary mechanism well defined in time. Next slide, please. So from the UNDR perspective, taking in account this context and the systemic nature of risk for us is a very, very important priority to improve the understanding of this multidimensional nature and the systemic nature of risk. This is the only way we have to improve or to support a truly disaster risk reduction action in the world. We also need an interdisciplinary approach between different sectors, education, infrastructure, telecommunications. I wanted to mention here that we need to support the construction of this bridge between science and technology and the decision-making world. And one of the main components we can highlight on the side of science and technology is all the advances that are being done on the use and the value add of 2D satellite imagery in different ways, not only for disaster risk reduction, to inform decision-making processes, but also in response, as you know, the different mechanisms as the international charter for major disasters, the Copernicus system. Also inside the UN system, we have UNOSAT and UNOSAT that are producing real-time products to support the response phase to disasters. We see also that I don't know if we can talk today about the post-COVID because we are still in the COVID era, but the recovery of COVID is an opportunity for a greener and more resilient recovery. We are taking based on the principle of building back better and take the opportunities of the after disaster process and then reconstruction process to integrate ways to improve the effect of new disaster in the future. And as I said on my last slide talking about governance, we can have best technology, we can have a real contribution from science and academy, but if we don't have a very well-designed governance mechanism at the national level, nothing will happen. So we need to improve this. We need to support national reforms on public policy to ensure a real disaster risk reduction and a real decision-making processes risk informed. Thank you.
Thank you, Carlos, for this talk. So our next speaker today is Dr. Raghavendra Singh from the Indian Space Research Organization, and he will talk to us about satellite-based assessment and forecasting.
Thank you, Cindy, and good evening to all of you, and namaste from India. I represent Indian Space Research Organization, which actively works in the field of disasters. Today, I will be sharing upon my team's experiences in ISRO related to satellite applications for flood assessment and forecasting, how we do such kind of work in our country, because our country, we have a lot of floods, and flood is a common and frequent source of disaster in India, and around 40 million hectares area prone to flood. Since we are a tropical country, obviously we have a lot of extreme weather, cyclones, and they result into this flooding condition. And you can see in the right side curve, the historical trend suggests that the damage due to flood and heavy rains varies from say 20 lakhs hectare to goes up to 160, 180 lakh hectare, depending on the kind of situation in that area. And it happens annually and all the time. So it is a big challenge in India, and it is taken very seriously from different sectors. And that's why different agencies from India Meteorological Department, the Central Water Commission, Indian Space Research Organization, and other research institutions seriously take this matter, do researches, and come out with solutions and bring out many management solutions to this problem. But in my opinion, the toughest challenge in this field is near-time assessment, and that too high spatial resolution. Generally, when it comes, you have to know where it is, and at particular that time, satellite has to be there, what is there in the data area, and how much area it covers, and that will high resolution, because to bring out any solution, you have to reach that place and see that how, this thing can be improved upon. So in that sense, you'll find that synergistic use of optical, synthetic aperture radar, the microwave scatterometer, radiometer, altimeter. So all has to come together, many of these satellite systems, to solve this problem, because individual system has its own limitations that we have gone through and found it out. So, and not only the satellite, what we found and what is the actual is that satellite can't be available all the time, but the information requirement is very high. So we have to integrate the satellite products with the hydrological modeling, as been already discussed by the earlier speakers. And that is the integration is the solution. Then only we can forecast and probably provide solution. Next, please. If you talk about India, major flood in India, the damages from the flood comes from the river floods, particularly the Ganga and the Brahmaputra river of northern Indian region, where most of the population also exists. And they are the major floods come every year as compared to peninsular rivers or river due to flood due to cyclones. In fact, you can see the right side curve. This has been prepared by our team, taking satellites daily observations from 2013 to 20. And all these regions, bluish region you can see, are the region which are inundated any time in a year. And this is a general picture of 7 to 8 year average picture. So, as I said, our country is prone to flood. So, what we do next, please. So, we monitor these floods continuously, particularly in monsoon season, or whenever the cyclonic and those activity come. Optical data are known to be, have a very good, what you call observation and resolution, I would say, whenever they are available. But at the same time, you'll find that they are not, they are less useful in the disaster of flood, because flood is associated with the clouds. You can see a picture here. I'm just showing a case study of a major flood in Ganga in 2016. And when we observe the optical data sets, you'll find many data sets with the cloud on it. So it is difficult to see beneath it. But then the solution is go and analyze more and more data sets and do the compositing of it. Once we do the compositing, we are able to get those flooded inundations. And you can see a picture that in May 2016, the river was flowing very, not much inundated. Suddenly in August, it got too much inundated. And even we found that inundation went to very high, 10 to 20 kilometer, spread around the floodplain of the river. So optical data are very useful. Only when you use in a composite manner, when you have many more satellites and do compositing. Next, please. Next, please. But the real use in the flood situation is the microwave observation, because you all know microwave signals are larger in wavelength, so they are able to propagate or penetrate the clouds, and they are not influenced by, I would say, atmospheric condition, cloudy condition, and you can see the flooding conditions in all weather condition. Even you can see day and night if you are using the active microwave emissions. So that becomes the most handy and more useful. And you can see that I'm just showing you in the center, the India, the different flooding regions, the flood prone areas, calculated from a AMS RE2 passive radiometer, which gives observation at 10 kilometers, but daily you can get. But at the same time, we show you the Sentinel or other radar data sets over Ganga, Brahmaputra, Kerala flood, Gujarat flood, and there was a flood in last year in the Bay of Bengal in this May 2020. So all this can be easily picked from this synthetic aperture radar, and this is being done regularly for all the floods. And ISRO monitors them with the help of the state agencies which are involved in the management. And this is a operational requirement as well as operational work done by ISRO with help of state disaster management authority. Next, please. Yeah, even the altimeters, which are satellites which do not give you images or picture, but they give you water levels. You can compute water level wherever this passes of this takes place. So we have devised a method where around 100 or that kind of location, we are getting regular water levels from satellites. And whenever you see deviations in the water level from their mean tendency, obviously those period you can easily pick it out. So this is another way of picking floods. Although revisited 10-day in this case, but it helps in picking those, and it helps in running the model, because when you run the model, models provide you water level and discharges. So it gives you a verification as well as a data for assimilation, and so that your model get corrected to the right path. The potential is detect water level, challenges is low revisit and suitable for only large rivers. Such techniques are only for large rivers, but yeah, these two help. Next, please. Now I'll talk about, by now I was talking about how the optical data sets and the synthetic aperture radar data sets provide information. Even the altimeter provides you with information. Now, getting information from satellite is one thing, but for disaster risk management, we need to know what is going to be the inundated area after say a day or 2 day or 3 day advance. That is forecasting. That can only be done when you have a hydrological model. So we have set up this model. We are working on this, this problem. And operationally, we are monitoring this Brahmaputra River, and we are running WRF hydro model. And this model has a capability to give forecast of river discharge at even before three days, 72 hours. And we have devised a method by which what we have done, we have recorded the majority of past floods in Brahmaputra through synthetic aperture radar, created a history of it with different water levels. Now what we do, we forecast the water level or discharges from the hydro model, WRF hydro model, and use our historical understanding that whenever this was there, this much used to be inundation. And you can see in the right, we are giving you the inundation probability. And we have also checked it in top, right top, you can see inundation probability given by the model, forecasted sort of thing. And in the below to it is the actual from synthetic aperture radar. So such kind of approach we are developing. And we have tested and working on this line from Brahmaputra, it's working well. We are extending over whole India this kind of approach. The broad idea is that you have a forecasting model from, currently we are depending on WRF hydro and a historical understanding of from satellite data. By that, we can forecast. These products are openly available in a Vedas web portal of ISRO. You can find its address here, https://vedas.sac.gov.in. You can go and you can see in the hydrological section of this web page past events of floods and the model running in real time and many more applications which can be done, which is being done by in field of hydrology over Indian domain. So anybody interested, probably you can visit the site and see many more examples. Because of lack of time, I am only showing you the brief overview of what we are doing. Next, please. Before I conclude, since this workshop deals with the water quality, I thought to discuss one example where I worked, where the landslides after the earthquake also changes the water quality. Water quality changes because of various regions. But we found in 2017 November, you can see a Brahmaputra river. Color changing is from 20 milligram per liter of suspended matter to 250. What happened? So there was a earthquake and a big landslide, and a lot of debris and those kind of things came into the river, and river became muddy. We analyzed this picture. So such kind of disaster-driven changes in water quality, which are very strong in signal, it's possible to see. In the right curve, you can find there are two images you can see. These are images showing the capability of satellite data to see that how we can detect the turbidity or the suspended sediment concentration. We also saw in our earlier presentation, this is the capability. Satellites can detect the turbidity, the suspended sediments, and chlorophyll. These things are doable from satellites. Of course, one requires hyperspectral satellites to do further work on that line. Here, what you see that during the last year, because of COVID, there was a lockdown globally and as well as in India. And due to lockdown, we found a patch. I'm just showing a patch of Ganga River, where you can see there was a sudden decrease in the suspended sediment. The river became clean. It was well reported and seen from satellite. So the Earth observation system here, I mean to say, has a good potential to monitor it, watch it, and in our country, we are doing it in a organized manner. Next, please. So just I conclude my presentation by saying you that real-time and accurate prediction is important, is challenge, and monitoring of simultaneous measurement, of course. What is our experience is that it is not only one or two data, we have to use all the gamut of data, optical, microwave, and altimeter, radiometer, because everyone has some advantage and certain limitations. So it is a more of an integrated measurement. And in future, this radar is going to be embedded with the altimeter in interferometer mode, and we are going to get a direct product from what you call river discharge from SWAT mission. Such kind of concepts are coming up, and we have to work on that line. We are working on that line to more and more quantify the hydrological variables. And just to conclude before that, we have to understand the various processes like atmospheric, river, and many processes like that, which where the long-term transport of vapor or the moisture do come and give extreme rainfall, that need to be handled, monitored to have a better prediction. Thank you very much.
Thank you, Dr. Singh, for this great presentation. So now I would like to open the floor to questions from the participants. So feel free to post your questions in the chat. So while we're waiting for questions, I have a question for Carlos. So what, according to you, is the best way to ensure effective disaster risk reduction and resilience building?
Can you repeat the question, ma'am?
Sorry, I said the question was for Carlos. I don't know if he's around. Yes, Carlos.
Yes, I'm here. As I mentioned in my presentation, I think the most important thing is to integrate at different levels the systemic nature of risk and the systemic way to analyze and assess disaster risk at global level. This is the only way to really contribute to an improved risk information, and to ensure a more resilient way of doing the disaster resolution across the sector and the scales, taking into account the effects on the economy, on the education, etc. So the systemic approach itself is the best way to improve the disaster risk reduction action. This is our point. Thank you.
Thank you. And following up on that, how is the UN disaster risk reduction supporting a truly disaster risk reduction, like risk-informed action, what you talked about?
Yeah, there's different ways we're supporting this. First, and taking account the priority one of the Sendai framework for disaster risk reduction, the understanding of risk, is supporting science and technology groups that are producing information. We have what we call the STAG, the Science and Technology Advisory Group, that is confirmed by different entities of science, technology, research associations that are producing information, and they're contributing a lot to inform different processes. And the other point we're supporting is the construction of this bridge between science and technology and the decision-making world. So making this first one of the goals of the Sendai framework for disaster risk reduction, that is the support for the elaboration of national and local disaster risk reduction, that needs to be informed with real evidence that comes from science and technology. So this is the second way. And third way is supporting also the national development plans. So the idea is to include, to mainstream the disaster risk reduction into the development DNA. So really working closely with countries and intergovernmental organizations at sub-regional level to inform the development plans and the development process, including the climate change and disaster risk reduction aspect as a priority on those plans.
Thank you, that's a great answer. Again, so feel free to post your questions in the chat for both of our speakers. So I have a question for Dr. Raghavendra Singh. So what is the status of a near real-time remote sensing data for addressing flood?
Okay, the real-time, as I said, data is the most important. And when you think of disaster like flood or any other disaster, at the moment, people generally depend on Sentinel globally, which is around 6-day, or Landsat, which is 16-day. So getting real-time data is a difficult task at moment. But this international charters, whenever disaster is activated, ISRO is a part of those that particular 17 countries which are supporting this international charter. And there, whenever the disaster takes place, it's activated, and most of the space agencies, including ISRO, they contribute data, and we are able to get many satellite data from various agencies in a single day. So in those situations, I mean, through the global cooperation, things are available. But in general situation, it is still dependent upon a few satellites globally, a Sentinel and Landsat. Although ISRO has our own fleet of satellites, so we get the data. But globally, people depend on these two kinds of satellites. And this is the general state of affair in the. But so in future, in fact, this constellation has to go more and more, and that is I personally believe it will be there more, and that is the way we can get solution and get real-time data.
Do you think that this could be improved with like with Landsat 9 that just came out, like the flood forecasting?
Yeah, in future, I mean, as the data comes more and more, not only from satellite, even the ground network also has to be assimilated. So the global initiatives from the ground as well as satellites with the appropriate model is the direction in which this disasters has to be handled in future globally.
Thank you.
Thank you.
So we have time for maybe one more question from the audience.
Yes, indeed. Hi, this is Apostolis Dimas. You have some time. I'd like to ask Carlos to share his insight in the area that he works in respect of water quality, let's say, hazards, and how, for example, those are part of the overall agenda, or whether they are part of the overall agenda of UNDRR perspective.
I was having a little audio trouble, Apostolis. Could you please repeat the question?
Sure. Can you hear me now? Better.
Perfect. Just disconnect my headphones so I lost the audio.
I wanted to just I'm wondering how water quality related threats are dealt within UNDRR. I mean, how integral are in the agenda and within all the other natural, let's say, risks and natural disasters that you're dealing with. So,
yeah, one of the points I can mention directly related to water quality is that, as I mentioned in one of the answers I gave, we're trying to connect disaster risk reduction with development. Development means improve the quality of life of people in different contexts, and particularly in development countries, and more specifically in the Caribbean, we are trying to improve the water availability, potable water availability for people. So that's related to water quality. What we do is to support the national and local development plans that include this sector as one of the sectors that. Then, in SEDEMA and in SEMADEM, in Brazil, we are actually working on information on water quality, and they are using, I don't know exactly the progress of this specific project, but they are using satellite imagery working on water quality, and it is linked to the disaster risk reduction activity project. And also we're closely working with UNFCCC that are in charge of the implementation of the Paris Agreement and the national adaptation plans on nature-based solution proposals that are directly linked to the improvement of the water quality in different sectors, and particularly in the Caribbean with the quantity of potable water of are really critical. So these are two points I can mention that are directly related to water quality and disaster risk reduction under the mandate of EU and the ERR.
Thank you. So we have a question for Dr. Singh from Klaus from the CSIRO. So he asked, satellite-based data might not be sufficient for real-time flood forecast. How well would hydrodynamic modeling and or machine learning, assimilating remote sensing, improve forecasting your case studies?
Okay. This question is very pertinent, and thank you for asking a very good question to me. In fact, the same difficulty or same challenges we are facing, and whole global community is facing, who are using EO data. EO data is good, but then getting real time, you are lucky. Many times you may not be, because disaster is a fast phenomenon, fast repeat phenomenon. In that case, as I was suggesting in my presentation also, the hydrodynamic model is the solution. But then the hydrological model also has to be accurate and should have a good skill of prediction. So what one does, one has to work upon the line, and which we are also working. As I just showed you one example of Brahmaputra River, where we are merging the hydrological model, which has hydrodynamic component, and the satellite data sets, and trying to forecast over 30 days. But we are, but as the question is asked, this machine learning is the future direction in this field. We ourselves are working in this direction, and all the historical knowledge derived from satellites available in different disaster situations, and the modeling outputs and the ground information, we are all assimilating together through ML, this machine learning, and this is the way in the future, and we are working in this direction. Thank you very much.
Thank you, and thank you to our speakers. I will let Samuela take the mic again and lead us into our mini break.
Thank you, Cindy. Thank you to our speakers, and thank you to all the attendees for the questions. So yes, we have a little break now. So it's 2:25 in London. So we will be back at 2:30, 5 minutes. And then we will move to the third session of today, where we will use in a collaborative tool called Group Map. And you'll see the link in the chat in a moment. And the session will be moderated by Catherine Cross. So see you back in 5 minutes. Thank you.
Okay, good evening, good afternoon, everyone. Good morning. So I'm going to start the next session. My name is Catherine Cross. I'm working as a consultant for the International Water Association, and I'm based in Bangkok, Thailand. I've put a link in the chat, which I hope that everybody has seen. I'll just put it in again. So this is the group map that we're going to use. So all you have to do, I think, is just enter your email address, and then you can enter that. But I'll just give a short explanation of what we're going to do, and then proceed into the exercise. If you have any questions, feel free just to ask or write a message in the chat. If you aren't able to access the group map, then just please feel to write your responses or your thoughts in the chat as well. We'll record all of that. So the purpose of this interactive session is to get your feedback and inputs on key components for a forecasting-based disaster risk management service. So as you heard earlier on, one of the areas that PrimeWater is focusing on is disaster risk management for harmful algal bloom outbreaks. And as I mentioned, we're going to use this cool tool called Group Map, which the idea is to get your inputs and also stimulate discussion. So we'll use this information to help develop PrimeWater's disaster risk management service, and the idea is to use repurposed short and medium term water quality forecasting information. And then just so you know, what's going to happen with this information is that what's gathered during the discussion today will compile into a report and share with you. But there's also opportunity for continuing the discussion and continuing engagement beyond this session, which we can share. And this could be through PrimeWater, but other initiatives such as AquaWatch and IWA. We'll start with some. So as I said, you can access through the link that I put in the chat. You just need to enter an email address. And we'll start with some questions to get an idea of who is joining today. So we'll do some stakeholder mapping. And then we'll have some questions on parameters and indicators that can be used as proxies to describe phytoplankton outbreaks. Then thresholds of the top parameters and impact indicators across sectors to describe the impact of these outbreaks. And finally, barriers. So at the end of this interactive session, we'll have some time for discussion. And yeah, so I think without any further ado, we will just move to the group map. So as I said, if you've clicked on the link, or you can just go, if you're using mobile phone, for example, you can go to join.groupmap.com and enter this code. So I am going to switch there, and you should be seeing a, sorry, just hold on a minute. I'm going to switch to the group map. So yeah, you should be seeing a matrix. And so what we want you to do here is to place your organization in the quarter of the disaster risk management matrix where it best fits in terms of your core business. So this is, we've got risk knowledge and analysis. And we've got about 5 minutes to do that. So that's understanding risks in an area, monitoring and warning services. So providing information to relevant authorities on water-related hazards, response capability. So this could be response on the ground or coordinating response in the event of a disaster. And then finally, dissemination and communication. So coordinating communication between stakeholders and to the public. So I'm just going to give people a few minutes to enter the information. So I can see we've got some people on here, but again, we encourage you to click on the link that I put in the chat, which I'll just add again. And just go in there and just start indicating where you think your organization fits. I'll just go back here so we can see some different organizations putting their information in. So just give another couple of minutes for people to add where they think their organization fits in here. And again, if you're more comfortable just writing that in the chat, please do that as well. Okay, I don't see any other people putting in information, but maybe I'll just wait a few more seconds before moving to the next question. As I said, you can put your organization in more than one of these quarters if you feel like it's relevant. Okay, I think we'll move to the next question because I don't see any other people putting things in. So I will bring you to the next question. So in here, we have some questions to better understand if your focus is more in rivers or lakes and reservoirs. Sorry, in rivers or lakes and reservoirs. And then we've got some questions to understand the level of engagement that your organization has in early warning and how important early warning is for your organization. So you just slide this along here, and then for the first one, you just select one or both. Okay, so this is our results. Okay, so I'm now going to move, before I move to the next set of questions, I'm just going to talk a little bit about, I'm just going to provide some context on how water quality forecasts are expected to be used for disaster risk management. And maybe I wasn't here for the early part of the session, so perhaps this has been touched on, so I'll just go through it really quickly. So probably as many of you know, the most common are nowcast-based early warning, so using grab samples and lab analysis, monthly sampling campaigns. And the results are algal alerts as they're happening. So this is when reactive measures can be taken. So what's being explored in PrimeWater is the use of deterministic forecasting based early warning. So using modeled measures of physical, chemical, and biological contaminants and providing forecasts up to 10 days in advance. So this gives some information on the magnitude, when and where a hazard may occur. But then there's also probabilistic forecasting based early warning, which is similar, but it uses an ensemble of modeled measures and again provides forecasts up to 10 days in advance. And the difference here is that it provides the magnitude, when and where, and then also the probability of the hazard occurring. And then the final type of early warning being explored in PrimeWater is impact-based early warning. So this is using phytoplankton bloom impact indicators, providing forecasts up to 10 days in advance on the expected impact of the forecasted water quality hazards. So using things such as, using indicators such as the population that could be effective or loss in fish productivity or fish kills. So just with that context, I'm going to move back to the group map. So if you're still in group map, I'm going to move you to the relevant screen. So again, that's if you've gone out of group, that it's the same link that's in the chat. So we're now going to go to a very quick exercise on prioritizing. So I'm going to bring you all here. So if you're, here this first question shows a list of possible forecasted parameters and indices that could be used as proxy indicators when describing phytoplankton outbreaks. So for example, chlorophyll, which is here. So we're just going to give you a couple of minutes if you want to add any additional parameters or indices that you would use or you think are missing. So yeah, just give you a couple minutes to do that. Okay, I'm not seeing anyone putting anything else. We just had a couple of additions, so I'll just wait a few more seconds. Okay, I'll move you to the next step. So here, what we want you to do is to prioritize these parameters and indicators in descending order. So the highest priority at the top. And to do this, you just drag and drop. You don't need to drag over all the parameters. Okay, so yeah, this is the results of this is everybody's results consolidated together. And as I said, we'll share all this information in a report. Okay, so I'm going to bring you to the next question. So this is looking at how can a phytoplankton outbreak or harmful algal bloom be assessed against a threshold. So for the top two parameters that you chose as an individual, we'd like you to provide thresholds based on specific best practices or industry standards that you follow. So we have an example here on chlorophyll. So yeah, if you could just put in your experience here, that would be great. So we'll just give you a couple of minutes to do that, and then we'll move to the next part. Okay. So the next question is going to focus on impact indicators. But before we move to that question, I'm just going to hand to Apostolos to give a short explanation of what this means. So Apostolos, do you want to talk about this slide that's up?
Yes, Catherine, thank you so much. Well, yes, that's fine. So, well, Catherine described a stepwise approach that we are considering in PrimeWater as far as early warning system is concerned, starting from nowcast data and actually reacting to a hazard, and moving forward to forecast-based early warnings. Either those are deterministic or probabilistic. But beyond just indicating the magnitude of the hazard, or trying to predict the magnitude of the hazard, another further, let's say, another approach, another a logic that we'll try to investigate is whether we go further beyond the actual numbers of describing the magnitude into the actual impact indicators that can demonstrate how severe this threat might be to different socioeconomic domains. And that's because this way additional information can be inserted in the overall early warning system that has to do with the exposure and the vulnerability of the sectors experiencing the impact out of the hub. So that obviously can have great difference even between the same sectors, not to say between different sectors at all. So it's a completely the impact that can be incurred by the same hub event, for example, can have completely different meaning. Hydropower production, let's say, sector, than, for example, potable water treatment operations that they deal with and they're much more associated with public health issues. But even within the same, as I said previously, sector, facilities that can uptake water, abstract water, and treat water can even be among them distinguish the level of impact that we can have from the same event. So at the end of the day, what we would like to discuss here are ideas that can actually identify good possible indicators to take into consideration, describing the impact that is associated with a harmful algae bloom outbreak across different societal domains. And this is to make a connection with what has been presented in the previous talks. This is a clear, let's say, indication of how these particular water quality hazards appear to have this systemic, let's say, and multidimensional implication across so many environmental and socioeconomic domains. So, Catherine, having said that, I think we can just jump into the group map and see the questions that the screens that you have prepared.
Yeah. So if you go to again to the if you're still in group map, I'm going to take you to the next. I hope to the next exercise. So this is where we like you to suggest impact indicators, as Apostolos just described, across sectors that you believe would be able to quantify the impact of a phytoplankton outbreak or harmful algal bloom. So you can just click and then you just type the impact indicators that are relevant to you. And we've got some examples that are provided by sector. So we're just going to give you a couple of minutes to do that. And yeah, so we've got the potable water treatment operations, freshwater fishing or aquaculture operations, irrigation, amenity and recreation, and then hydropower production. But if there are other sectors that you think are relevant and impact indicators that are relevant for those other sectors, please just add in this last box here. Okay, we're not getting, maybe I'll just give a few more seconds in case there's any more additions. Don't see so many. Yeah, if there's interest in adding these, you can always go back and add your thoughts later. Okay, so maybe just for purposes of time, we might just move to the final exercise, which is on barriers to forecasts. Oh, I see people adding some, so I'll just wait a minute. Okay, I think I'll move us to barriers. So I'm going to bring everyone to this if you're still in group map. So here we want, just first of all, if you could add so there's a list of barriers to water quality forecasting and warning that have been added here. So if you have any additional barriers that you think are relevant to putting in place water quality forecasting and warning, you can just click on here. I can't add any more, but everyone can add up to 2 more ideas. So yeah, you just click on here and type in your suggestion. So just give you a couple of minutes to do that. Okay, I don't see anyone adding any more, so I might just move us to the next part. So again, similar to the previous exercise, we just want you to list the main barriers to forecast awarding from greatest to least in descending order. So again, you just drag and drop. And as I said before, you don't have to put everything in there. Just put the ones that you think are I guess, the most significant barriers to less significant. I'll just give you a couple of minutes to do that. Okay, so I'll just maybe move us to the results. So here we can see the consolidated prioritization or list of barriers from the most significant to, I guess they're all significant, but the most significant to lesser. So we hear, unsurprisingly, a lack of data or a lack of data or monitoring water quality parameters, because you can't measure what you don't know. It's one of the top barriers. Okay, so that actually concludes the exercises on group map. I will leave it open and I'll unlock it. So if any of you want to go back or add anything, you're welcome to do that. If you didn't feel you had enough time, or you want to take a look at it later, we'll leave it open for a couple of days. So we do have time for a short discussion. So I'll just put up the questions on the screen. So we've got about 10 minutes, 10-15 minutes. So I think I will hand to Cindy to facilitate the discussion, and we have some questions that have been put forward here. So Cindy, if you're still there,
Katrina, I think Cindy connection broke, so maybe you can facilitate this discussion.
Yeah, sure, no problem. Okay. So, well, if you feel free to unmute yourself and answer any of these questions, or you can also write your thoughts in the chat. We'll just do this for a few minutes. So we've got a series of questions, I guess, related to some of what we've been asking in the group map. And the first one is, we wanted to get some thoughts, or if you could share experience of proxy indicators and their thresholds that you have been used to describe and assess water quality or water related risk. Okay, this question it's quite specific. So maybe we can come back and I can move to the next one. So the next question is, what are your experiences of different impacts of water quality related risk across sectors? So this goes back to the question that was asking about impact indicators that can be provided for different sector. And we'd like to get your thoughts or reflections of how water quality risks can impact different sectors in your experience. So like, I think, for example, what Apostolos was saying before, obviously the hydropower sector would have a different experience compared to water treatment, the potable water sector, because there's obviously increased costs and need for chemicals and energy when there's a harmful algal bloom. Okay, well, maybe I'll just go through all the questions, and then if there are any inputs, we can stop there. So the next question is on what are your experiences in defining and deciding the impact of a water quality related hazard? So this question is thinking about like how do you decide what the impact is going to be? Like how you decide what you're going to use as the impact indicator, and why how is that decided? It's probably more of a policy type question, but and then the final question is, well, we already reflected on this, but on the barriers, but also what are the enablers to forecast and warning, and how can they be addressed and enhanced?
Catherine, this is Apostolos. Well, I think as we are approaching to conclude this workshop, I think that it's fair to say that, I mean, the over disaster risk management continuum has a large chain of actions, starting from disaster risk reduction, anticipatory work, and goes to response and recovery activities. I think it was really nice to keep from also from the talks that we had, that a part of the technological aspects that PrimeWater focuses, and this is more or less associated to the very first, let's say, level of this risk management continuum, which has to do with the disaster risk reduction through an early warning system. I think it's nice to keep the importance of all the other, let's say, constituents, the governance, the institutional aspects, and I think that was made very clear from the nice talk we had. So this is clear, and this has to be clear that PrimeWater has a technological focus on how to support decision making within the DRM activities, on how to provide decision makers in this field with strong and robust forecasts to make decisions, to trigger actions, to trigger efficiently and in advance actions, anticipatory actions, in order to reduce the risks, in order to reduce the impacts that, in our case, water quality threats can impose to so many different, let's say, sectors. And I think it's important, and that was to say that PrimeWater has a lot to learn from this sector, from this angle, because of the experience that has been accumulated, unfortunately, global experience in dealing with so many other natural disasters, including flooding or water scarcity. There are a lot of practices around the globe that look in this direction, and the intention here, from our perspective, from the PrimeWater project, is to initiate a discussion, to make a connection, establish a connection between what PrimeWater is dealing with, and this is water quality related hazards, with the experience that has been accumulated in dealing with other types of natural hazards. And I think that was a very nice step, a nice initiative that hopefully will be followed by others. PrimeWater can serve as a platform for this discussion, but also IWA has established a working group on Earth observations and water resources management that can actually support this discussion even beyond the lifespan of this project. So there is a lot of technological aspects as well, open, as Dr. Singh nicely pointed out. Synergies between technologies, different technologies, are important and can have an adding value at the end of the day. And I think these are the key, let's say, nice points that we can actually keep from the discussion on that there are strong possibilities, technological possibilities that has to be tailored in order to support decision making in a better way. And I think Catherine, that from my side could be a summary of some key points discussed today.
Personally, I believe that you were asking about some of the questions. The barrier-wise, I personally believe that lack of data is the barrier. Unless it is improved upon, the forecasting skills will lack it, because they are directly proportional. Although forecasting depends on a lot of physics you do and a lot of processes you develop the models and computer things, but ultimately it is the data. So lack of data. Now data can be ground, satellites, airborne, whatever it is. As far as Earth observations things are concerned, as I was mentioning in my talk also, there's a long way to go. And this has to be improved. And I believe that the international participation, global participation from UN forum or various forums on the water, as you yourself are doing these activities, we're going to enhance this activity, going to give a impetus to this task, and more people will come together. And that is the way, because it is the pooling of ideas, pooling of people together, which obviously would develop these methods, try to harmonize the data sets, and there the solutions would come out. So it's ultimately international partnership, where everything, the best example is like WMO. There's a beautiful network of observation being collected for meteorology. That's why the meteorological forecasts nowadays are quite accurate and very nicely done as compared to long back. Similarly, in hydrological perspective also, there has to be similar network from different countries, different places, different groups. That is one thing I believe would take place. And as far as EU is concerned, Earth observation system, I see like there's a beautiful concept called A-train, atmospheric train, where different satellites are there having LIDAR, the radar, whatever not, and they all move within 15 minutes at around 1 p.m. In the afternoon and collect a lot of observation in synergy in the form of constellation. Similarly, I think that in future, when most of us, the different space agencies of the world, they come together or think of having a constellation of satellite, call it similar like hydrological train or something like that, which would be a cooperative movement. Obviously, it should have various instrumentation, just like the atmospheric train is available. Since here it is water and you need more high resolution images also, which do not require atmosphere. So it was feasible for atmosphere to develop that kind of train. But in my opinion, in future, hydrological train, H-train sort of composition, the constellation through global participation is some of the area where such thing obviously will provide better data for assimilation in the model and the improving the forewarning of the system. Thank you very much.
Thank you so much for this contribution, doctors.
Yeah, thank you very much. That was very insightful to have that. Well, I think we'll wrap up. Apostolos has already given his summary. Before we go, we just wanted to share some information. Another point from the PrimeWater project is that we're undertaking Samuel has just shared it, that we're undertaking a survey. And the survey is to gather information on user preferences for Earth observation services. And it's really important to get your inputs because it helps to understand like what are the attitudes, what are the obstacles, like we talked about some of the barriers just now, and what are the drivers in using and choosing different satellite derived water quality products. So the link to the survey is in the chat. And if you want to get an explanation about the survey, like the methodology, there's a YouTube link, which we can also provide as well. There's a little bit of an incentive. If you're able to complete the survey, you can get a 10% discount on IWA membership. But of course, we hope that you complete it as a way to contribute to the knowledge in this sector. So I think from that, we will close. So I'd like to thank everybody for joining today and staying for the session, and the speakers especially for providing your inputs and contributions. And as Samuel has put in the chat, there's a few more sessions this week. Tomorrow is on potable water. It's at an earlier time so hopefully we get more people from where I am in the world. And we hope to continue involving you in these discussions and having your contributions.